Welcome back, everyone. So, you know those AI code assistants that are pretty much everywhere now? Ever wonder what's actually going on inside them? Today, we're going to pop the hood and take a look. We'll trace their entire life cycle, guided by 4 really fascinating new papers that cover everything from super stealthy data attacks and developer rights, all the way to building hyper-efficient models and even teaching robots to learn from their mistakes.
Exactly. It all feels a bit like magic, right? You type a comment and boom, perfect code appears. But what's really happening inside that black box? We're going to trace that whole journey. How is the data gathered and kept safe? How is the AI's actual brain built? And what happens when the code it writes has to do something in the real physical world, like control a robot? Let's get into it.
Okay, so every AI journey starts with one thing: data. And our first paper, which is called Detecting Stealthy Data Poisoning Attacks in AI Code Generators, shows that this is exactly where some of the biggest problems pop up. We're talking about 2 huge issues: security and ownership. That's right. The researchers point to this really sneaky type of attack called data poisoning. And there's a new version they've found that's, well, it's pretty concerning. It's called triggerless poisoning. Just imagine an attacker slipping a piece of vulnerable code into the training data. The tricky part is it looks and acts almost exactly like the safe code it replaced, but it has a hidden security flaw. And since the description of what the code does stays the same, it's practically invisible to normal security checks.
Okay, hold on. What makes these triggerless attacks so much sneakier than the older methods? Well, it really is all about that trigger. The old style of attacks needed some kind of obvious hook, like a weird keyword or a strange comment, that security tools could pretty easily scan for and flag. But these new attacks? They don't have one. There's no trigger. The model just quietly learns a subtle connection between a totally normal request, like, hey, create a file uploader, and the attacker's hidden, vulnerable code. There's no weird pattern to catch.
And the scale of the problem is, it's big. The researchers put current security methods to the test, and the results were, frankly, not good. Their effectiveness is measured by something called an F-score, where 1.0 is a perfect detection rate. As you can see, they're not even close. The very best method, static analysis, only hit a score of 0.70. And get this, that was in a test where a whopping 20% of the data was poisoned, which is way more than you'd likely see in a real sophisticated attack.
Wow, that is a huge security hole. But it also brings up a totally different question for me. If the data itself can be manipulated, what about data rights? Like, if you're a developer and you have public code up on GitHub, how can you possibly know if your work was used to train some big commercial AI model, maybe without you even knowing?
That is the exact problem that a second paper called RepoMark, a code usage auditing framework, sets out to solve. The researchers came up with this incredibly clever way for developers to essentially put a watermark on their code. It's brilliant, actually. It works like this. First, you generate several versions of your code that all do the same thing, they just have different variable names. Then you publish one of those versions publicly and you keep the rest private. Later on, if you want to audit an AI, you test it with all your different versions. If the model is consistently more familiar with your public one, that's what's called a lower loss score, it's a very strong signal that it was trained on your code. And how well does this thing work? Incredibly well. The researchers found that RepoMark has a detection success rate of over 90%, and it has a false positive rate below 5%. This finally gives developers a real tool to demand some transparency.
So, okay, let's say we've got the data sorted out, both security and ownership. What comes next? Well, you have to actually build the model. And the big question here is, how do you make an AI engine for code that's not just powerful, but also really efficient?
A huge part of that answer is in something called code embeddings, which is what our next paper, Efficient Code Embeddings from Code Generation Models, is all about. Put simply, embeddings are just numerical versions of code. It's how the model translates programming languages into numbers so it can understand their semantic meaning, not just the text itself. This is the magic that lets you search a massive code base with a simple question in plain English.
And, the big surprise from their work is that bigger isn't always better. They built this small, specialized model with just 500 million parameters. And the result? On a whole range of code-related tests, their little model actually did better than a gigantic general-purpose model from a major tech company. It really seems like being specialized can give you a winning edge.
And part of their secret sauce was something they call instruction prefixes. So before they feed any text to the model, they add a simple little instruction at the beginning that tells it what kind of job it's about to do. Something like, find the most relevant code snippet for a code search.
This simple trick just primes the model, gets it in the right headspace, and makes it way more focused and efficient for that specific task.
Okay, so we've got our data and we've built our smart, efficient model. Now for the final and maybe the most exciting stage. What happens when the code this AI writes actually gets used in the real world? And I mean, what if it's controlling a robot? This is where our last paper, RoboInspector, comes into play. The researchers found 4 really predictable ways that AI-generated code tends to fail when it comes up against physical reality. The first one is exactly what they call it, nonsense. This is when the model just outputs complete gibberish or code that's invalid and the robot just can't execute it.
The second type of failure is disorder. This is when the AI knows all the right moves, but it gets the sequence all mixed up. A classic example is telling a robot to open its gripper to drop something before it has even moved over to the trash can.
Third, you've got infeasible. This happens when the AI cooks up a perfect plan for a robot that doesn't exist. It might tell the robot's arm to reach for something that's physically outside of its range. The logic of the code is sound, but the physics are just plain impossible.
And finally, there's the one that's the most subtle, bad pose. This is where the robot moves to the perfect spot in space, but its gripper or its tool is at the wrong angle. You know, it gets right up to the bottle cap, but it can't actually grab it because its wrist is tilted the wrong way.
That feels like a lot of ways for things to go wrong. Did the researchers find any ways to actually fix these problems? They did, and the solution was surprisingly simple. Just a basic feedback loop. When the robot failed, they just told the AI why it failed in plain English. And just that feedback alone was enough to boost the robot's success rate by up to 35%. It literally learns from its own mistakes.
Wow. So, okay, let's bring all this together. We've really gone on a whole journey here, from the raw data that an AI is trained on, all the way to the physical actions that its code can actually produce.
That's right, and the key takeaways are pretty clear when you lay them all out. At the data level, we've got this huge security challenge with stealthy poisoning, but at the same time, we're seeing these cool new tools that give developers power over their own data rights. At the model level, we're learning that smart, specialized design can be more important than just raw size. And finally, at the application level, we're seeing that to bridge that gap between digital code and physical reality, you need to give the AI a way to learn through feedback.
It's just an incredible look at the entire stack, from the very beginning to the very end. And it leaves us with this one final, really important question to think about. As these tools get more and more powerful and more autonomous, who is ultimately responsible when the code they write inevitably fails? That's definitely one to chew on. Well, that's all the time we have for today. Thanks so much for joining us.
Thanks, everyone. We'll see you next time.